All right, we have another Taylor Maclaurin one. And at first, when I saw that notation, I'm like, oh man, that looks kind of intimidating here. But then when I was actually working out, I was like, all right, we could handle this stuff right here. This could be a pretty good one for us. All right. So tells us a couple things. We know we're going to need that when we use that main definition for the Taylor polynomial. And then it gives us a notation for like the derivatives and stuff. It says for all the derivatives bigger than greater than or equal to 1. So like I could plug in 1, 2, and 3, get the second derivative, third derivative, fourth derivative, whatever I need there. Okay, so it says show that the first four non-zero terms of this Maclaurin series are that. Now that's kind of neat that they do that, because let's say you had trouble doing part A, you could still take those four terms right there, and when you see that integral on part C, you could integrate those few terms, and then boom, you have part C down, right? And you could also look at this and get the general term for this one right away, but we'll talk about that in a second. And so this is kind of nice though. If you had trouble showing that, you could still do the other parts of that problem. So that's pretty good design there. Now for the first part, when it says show the first four non-zero terms of the Maclaurin series, okay, so which means first four terms, a lot of times that might be like the third derivative, fourth derivative, whatever. So when you start doing this Taylor polynomial or Maclaurin series, like let's start off with that main definition for your Taylor polynomial: f of 0, f prime of 0, x minus 0 to the first over 1 factorial, a double prime of 0, x minus 0 squared over 2 factorial, and so on, right? Just like your main definition from your videos. And then since they told us f of 0 was 0, so then boom, one term is going to be gone right there. So that means I need go to that fourth degree to get my four terms right there. Now, you might not know that at the beginning, but you know you're going to need some derivatives, right? And so to get the second derivative, third derivative, fourth derivative, here's what we got to do. So if I want the second derivative, that's when n is equal to 1 to make that a 2 right there. So I just took n equals 1, plug that in right there. So I got -1 times the first derivative at 0. So -1 times f prime of 0. And then they told us f prime of 0 right here. They told us flat out that was equal to a +1. So -1 times a +1 gives me -1 for that second derivative. And then when you want the third derivative, that's when n is equal to 2. So simply plug in n equals 2 to that formula. So I'm going to get a -2 times the second derivative at 0. So I'll go -2 times the second derivative, or f double prime. And then that's what you found right here was -1. So you get +2 for that. And then for the fourth derivative, you got to plug in n equals 3. So you'll go -3 times f to the third derivative. And the third derivative is that 2 right there. And then you're going to get that -6. So then once you obtain your few derivatives right there, so sometimes they give us a function where we take the derivatives on our own, but sometimes they'll give us a formula like that where you got to find them. And then, so you got your main definition of your Taylor polynomial, and then just plug that in for the second derivative, plug that in for the third derivative, plug it in there for the fourth derivative, and then there's your Taylor polynomial. Then you could just simplify that a little bit. They tell us that's equal to 1. We figured out what these were, and so that's just like -1/2. And then you got 2 over 3 times 2. The 2's will cancel, you get 1/3. You got 6 over 4 times 3 times 2 times 1. That's 6 divided by 6. Those will cancel out. So you're just going to get the -1/4 right there. And then this is what they kind of had us showing, and we did get that, so we're happy. And then notice though, you got to keep reading here. It says write the general term for that Maclaurin series. And this is also something, even if you had trouble with all of this stuff right here, you could still get this general term just by looking at those terms there and those terms here. I think this is an easier one. We kind of see what's going on with that. This is x to the first over 1, x to the second over 2, x to the third over 3, x to the fourth over 4. So that's just going to be x to the nth over n. And then you notice that it's alternating. So that's either going to be your -1 to the n or -1 to the n plus 1 notation. And this one's starting at n is greater than or equal to 1 for these derivatives right here. So what we want to do is, like, if you plug in 1 for the n, then you get -1 squared, which would give us a positive first term right there. All right, and so we know it shows that correctly. All right, letter B says, does it converge absolutely conditionally? All right, so this is your absolute conditional convergence. You could watch a little 5-minute video clip of a review for that. We also have that yellow handout with a bunch of examples on there. And I think I may have even made the handout so good, I think this exact problem might be actually on your handout right there. But conditional absolute convergence, here's what we're going to do. You first got to do your normal converge diverge stuff right there. So we know this is an alternating series, and well, it tells us that x equals 1, right? So it starts off as a power series, but then they tell us x equals 1. So when you take the 1 and plug it in for the x, it becomes a normal series just with ends in there. And that's an alternating series, okay? That's a convergent alternating series. You can kind of do that work to the side if you need to, or you could even do that work in your head, but that's a convergent alternating series right there. We did limits n approach infinity of that nth term, that was equal to 0, and then the a sub n plus 1 was less than the a sub n, so that 1 over n plus 1 is less than the 1 over n, and that's true since n plus 1 is greater than n. So that's your alternating series that we did before. And then when you check for conditional or absolute convergence, you got to now do the absolute value of that thing and see whether that converges or diverges. So if I do the absolute value of that, all that's going to do is make the part that's negative and make it positive. So that's always going to be a positive 1 over n, which is a divergent p series. So if you got that both of those converge, then that converges absolutely. But since this converge and the absolute value diverge, that's when we say it converges conditionally, since the original series converges, but the absolute value of the series diverges right there. So if you need a little refresher on that, watch a little 5-minute video over converge diverge and check out that handout I gave you with a bunch of examples on there over the conditional and absolute convergence stuff. All right, now letter C. I like letter C because I've been telling you, anytime you have a string of terms like this, and if you see in that problem a derivative notation, you're meant to take the derivative, or if you see the integral notation, you're meant to do the integral, okay? So you're just gonna integrate those few terms right there. Go x squared over 2, x to the third over 3, so that'll be x to the third over 6, x to the fourth over 4, so that'll be x to the fourth over 12, x to the fifth over 5, so that'll be x to the fifth over 20, and you could just straight integrate that right away. Now, they always use different letters there. We're not gonna be concerned about that, but just if you wanna do f of t, then you could just take that and then you could just make them t's, right? But see, you always put the letter that you want right there, because then when you integrate this, you would get the t's, but then you plug in the x's for your top number minus plug in the 0 for the bottom number, and you're going to get that. But it's just a matter of just integrating those few terms right there, and then you're going to have that. That's our g of x. But then what they also wanted was the general term. Now I went from hating those problems, because I would used to have to like force my brain to see the patterns, and it's tough for me to see the pattern sometimes when it goes like that. It's easy to see this pattern here, which is x to the nth over m, but I don't have to see the pattern here. You can actually integrate the general term. So if you want to, if this is your original general term, and then you're supposed to integrate that, you could straight integrate that general term. So that, I'm going to tell you that -1 to the n plus 1 will always just kind of carry down. So that negative notation is just going to kind of stay there. And then this is like x to the fifth over 5. So if I have like x to the fifth over 5, right? When I integrate that, that would have given me x to the sixth over 6. That gives me x to the 6 over 6, and that 5 stays there because that's just 1/5 times the integral of x to the fifth, right? And so when you integrate x to the n, you're going to get x to the n plus 1. But then you're also going to divide it by the n plus 1, and then that n, that's like a 1 over n or a 1/5 that's out on the outside right there. And then so that n just kind of carried down, just like that 5 just carried down, and you got that extra exponent there. So that's how I'm obtaining this general term right there. And I guess I got my work for it right here, but I just wanted to kind of do that from scratch real quick there. But I just took that general term, I did I just did x to the n plus 1 over n plus 1, like my normal power rule for the integral, and it gives me that general term right there. You just got to make sure you read too, to make sure if it asks for the general term, it doesn't always, but you make sure that you give that, or you give an attempt at giving that if it asks for that. All right, now letter D. This is something we're used to. This is just finding the next term. It uses the phrase alternating series bound. That's good. That's just going to be the next term in the problem right there. But notice how we do have an alternating series, and it goes 1/2, 1/3, 1/4. That terms decrease in absolute value to 0. So that's going to be our alternating series bound. It doesn't say Lagrange error bound or anything like that. And it says the word error. And then what this means is piece of n, the nth degree Taylor polynomial. So this means if I take 1/2 and I plug it into a 4th degree Taylor polynomial, that's the approximated answer we'll get. And if I take 1/2, plug it into the original true function, that's the exact answer we'll get. And then we just want to know what's the difference between that estimated answer on the Taylor polynomial and the exact answer on our actual function right there. So anytime you're doing the difference between your approximated answer and your exact answer, that's going to be the error involved. And we just care about the absolute value of that. But that's how I know if I'm using a 4th degree, and then when I do the error is going to be the next term, that means I'm going to need to use the 5th degree for the next term. So that's why it gives us the n as the nth degree. We're using a 4th degree, so the next term will be a 5th degree. And so we're just going to do the errors that next term in that pattern there. So since they use the 4th degree, then you're just going to go to that next term, that x to the 5th over 20, and then plug in that 1/2. That's your x value. So you plug in that 1/2, that's going to be 31 over 32 over 20. No, 32 times 10 is 320. So if I double that, because we're times it by 20, that's going to give us 640. So then you got the 1 over 640 is less than that 1 over 500. And we were supposed to show that that's going to be less than that. And you don't have to write down true since 640 is bigger than 500. But if you didn't get something that was bigger than 500, you know that's not true. So you just got to go back and kind of check your arithmetic there. Orchestra.